Hello, ladies and gentlemen. I am glad to greet you all here today. And in this lecture, we shall discuss different approaches to computer vision problems and actually make an overview of different problems in computer vision area. Of course, deep learning is really important for computer vision, but not only neural networks can do different tricks, so classical image processing is also very important. But in this lecture, we focus on deep learning based approaches and discuss what are the problems which are usually being solved using these neural networks, how actually people came to the current stage of the computer vision area, and what actually is the data sets we should think about when we try to solve our own problems, to pre-train our models, and so on. So let's start. And in this lecture, we have relatively simple structure. First of all, we discuss just in a broad way different problems in computer vision, how they actually formulated, how the formulation ever actually changed through the time. And after that, we switch to different approaches which allow to solve these problems. Also, we shall discuss the convolutional neural networks in general, once again, just to make a small recap, because last time we've spoken about them was really a long time ago. And we shall highlight main ideas from different famous architectures, which were really great in some tasks in computer vision. Of course, later we shall dive deeper in almost all of the techniques we will discuss today. So today we get the general view, general picture of the area, and later we shall dive deeper. And in the end, we shall discuss one of the really important parts in any part of artificial intelligence, especially in computer vision, the data sets. Just make the overview of data sets, because even if we have really brilliant, huge, and just awesome network or any other model, and we don't have any data to train it on, it's useless. So of course, we should know where we can get huge amounts of data to train the models we are going to discuss today. So let's start. And first of all, let's make an overview of different problems in computer vision. So there are many different problems, and all of them at first sight might seem like supervised learning problems. So classical problems like classification, or actually regression as well. For example, you can try to predict some kind of age from a picture and so on. But they're kind of simple. Also, there is a localization and detection problem. There is a localization problem where we need actually to localize one person or actually any other entity, object, thing, person, dog, cat on image. And detection where we need to detect several entities of the same type. Also, there are semantic segmentation, instance segmentation, image generation, adversarial text, and so on, so on, so on. So let's actually discuss them and provide some examples. What are these problems? Why are they actually different? What differences are actually under the hood? Which differences will we face under the hood when we try to solve these problems? And so on. The simplest problem is classification. I mean simplest because we are already familiar with it rather well. So image classification is one of the main problems the community has been focusing on for decades. And back in 2012, actually, AlexNet, developed by Alex Krzyzewski, whose thesis advisor was actually Geoffrey Hinton, developed a model named AlexNet, which succeeded in image classification problem on the ImageNet and just surpassed all other approaches. And actually, that was the moment when deep learning just emerged. So what we have? We have an image. Usually we treat an image as three-dimensional tensor of the quotes. So it has several channels. Usually it's one channel or three channels if we have a colorful image, one channel if we're speaking about just grayscale image, and it have height and width. So just different number of pixels for different sized images. And our goal is to predict some class label. We assume that we have finite number of class labels and we predict only one of them. To do that, we simply apply some kind of network or any other model which takes an image as an input, then predicts target value as an output, actually a distribution of all the possible class labels. And it's not different from text classification, vector data classification, any classification, because only difference is on the feature extractor side, where we usually use either CNNs or transformer networks or something like that. So classification is usually nowadays considered not as final problem because it's rather easy to train a classifier, but it's some kind of a proxy problem, a subtask in different problems like detection, localization, segmentation, prediction, and so on. So we actually classify whether this image does belong to some class, does it have some entities or not. And let's actually continue with localization, because localization is almost as simple as classification, but still it has a bit more complex stuff to do. So let's say instead of just simply classifying every image, whether there is a dog or cat on the image, we ask about where is exactly dog or cat or any other entity located on this image. So instead of predicting one class label, like in classification, we predict the bounding box. BB is for bounding box for this image, actually, for this entity on the image. And one can see that actually localization is definitely a regression problem, because we predict 4 integers representing just coordinates of, for example, upper left corner and bottom right corner, which actually defines the rectangle around the object, so we get the bounding box. And in localization, we really make one too strong assumption. We assume that there is only one object per image, so we always predict only 4 ints for every image. That's why localization nowadays is not so popular, and instead of that, people usually work on detection problem, which is actually almost the same as localization, but instead of one bounded box, we assume that we might see several objects on the same image, and these objects might be of different class. For example, on the image on the left, we can see that we have truck here, one bounded box. We have bicycle, another bounded box. There is a dog sitting in here. And for example, one could say that we have tree here as well. If our network was able and was trained to find trees on the image, it would show us that there is a tree as well, and so on. So detection is almost the same as localization, so it can be used in many different applications, like smartphone interaction, like you just detect something in the video while you open the camera. In biometrics, for example, we need to find the face on the image when you use Face ID or some other biometrical identification. Gesture recognition, for example, you show only one hand into the camera, and then the camera, the software and hardware actually detects the hand and then classifies the symbol the hand is actually showing. Robotics, just we need to track something around us, object tracking, and so on. Everything's the same. For detection, everything is just the same. So we just assume that we have several objects, we might have several objects on one image, nothing else. And even deeper problem, I mean even more complex problem, is semantic segmentation. So when we have been speaking about detection or localization, we were speaking about only bounded box around every object. So we need to find every object on the image, just select it, and that's it. But actually we can see that if we just select a cow, then in the bounding box we also will have part of the tree, part of the grass, part of the other cow, and so on. So semantic segmentation is more about assigning some class label to every pixel of our image, just like we have on the bottom. So actually in here, purple or something like that, grape color I guess, is assigned to trees, blue to the sky, green to the grass, brown to the cows, and so on. So while in detection we actually predict several bounding boxes for our class, for every image for different classes, in segmentation we actually predict class label for every pixel. So now on the output we actually have some kind of image as well. By image I mean just tensor of the same shape, same height, same width, but now every actually pixel is containing just class label. And of course one could think that wait, why do we have two cows on the image but only one cow area with two cows combined, connected together on the image? You're right, that's why instead of semantic segmentation, people usually nowadays speak about instance segmentation, which is almost the same as semantic segmentation, but now for every element we actually predict whether it's separate element, just separate bike, separate person, separate something, or just they belong to the same entity. For example, we have two motorcycles in here, but we can see that they're actually different motorcycles, and if we just assign these pixels the motorcycle value, then it would be the whole area of motorcycle. But instead of that, the network is trained to understand that this motorcycle and this one are different. So actually now we assign not only class label to every pixel, but class label and index of the entity of this class who found on the image. So main difference is that we predict separated masks for each distinct object, And of course, it can be used everywhere as well, like in biometrics. Once again, we found, for example, not image, but part of the image where the face is located. Robotics, robot just finds the ball, for example, to play football. Self-driving cars are usually instant segmentation all the time. They need to find other cars, pedestrians, signs, road signs, traffic lights, everything. Also, instant segmentation can be used to use some kind of enhancements on images. For example, if you take a look at some filters in Instagram or any other software to update your photos, you can see that they might make some, they can make face look a bit better in some terms. So at least they assume that these filters make the face look better with some makeup, for example. So first, the mechanism is actually algorithm is finding the face on the image, segment it, and then use some updates, some algorithms to make the image look better in some terms. Also, we can speak about image super resolution. For example, we find face of this person and we can try to increase the resolution using some kind of specific methods to actually recognize whether is that the person you've seen 2 years ago or not. Video recognition and so on. So there are really many different problems connected with instant segmentation, semantic segmentation, detection, and localization. But actually nowadays, people speak mostly about detection and instant segmentation because they're just broader problems. And usually they're being solved almost by the same networks because under the hood, we have almost the same transformations to predict either the bounding box or to predict the mask for every entity. All right, so here we go. But right now we were speaking only about taking image as the input and predicting some kind of markup like class label, bounding box, segmentation mask on the output. Of course, there are different problems where we have image on the output instead of the input. For example, we can speak about image generation. I guess you remember about the simple project. Actually, it's not so simple, but it's easy just to open it in your browser. This person doesn't exist, where generative adversarial network, which will be covered later in this course, are generating different images of people who literally don't exist. In image generation, we can take as an input just nothing, just for example, noise vector or just nothing, and generate some output image. Or we can take another image as the input, for example, and try to add some properties to this image. For example, style transfer from this beautiful picture to this photograph, where transferring style, or to this photo of Steve Jobs, or to this photo of some park, I guess. So image generation is generating some images of the same size they had on the input, or of the size we actually asked for, and that's kind of it. And there are many applications, like we can just make images better, like some enhancements, like we said, in different applications in our mobile phones. We can also use it to generate some data sets to pre-train our models. For example, we don't have enough data, but we have really good image generator. Then we just pre-train our model on generated data and so on. And of course, we can use these approaches for data augmentation. So instead of using original data, we can try augmenting it somehow. For example, remove some part of the image or draw another person in there, something like that. But of course, all the time when we're speaking about image generation, we should understand that if our generator is not ideal, and it's always not ideal, then the generated image will actually be different than the image that could be taken in real world. They're just from different distributions. One distribution from the real world is just real distribution, as one is only approximated distribution, and the quality of approximation depends on our image generator quality, number of epochs it was trained, number of parameters, and so on. So if you will ever train, and I guess you definitely will, some model on synthetic data, you should always remember that you are training the model on non-real data. So the data is synthetic, and you don't have any guarantees that actually model trained on synthetic data will behave with same quality on real data. All right, that's kind of it. And last but not least, topic adversarial attacks. They were rather popular several years ago. Nowadays, I don't really hear a lot about them, but they're really interesting, and we will speak about them as well, because adversarial attacks are really beautiful. And adversarial attacks are actually attacking all these computer vision systems into their heart, so they just break the mechanism these systems are based on. And for example, if we have some image classifier on the left, which sees panda on the left, and just add some random noise, which is almost invisible for our brain, for our eyes. We see that these pictures are actually almost the same, but for the computer vision model, here it sees panda with 57.7% confidence, and in here it's actually sure that it's gibbon with 99.3% of confidence. So actually this random noise is not so random, and it was generated especially to break this particular computer vision system in image classification problem. And of course, adversarial attacks can be applied almost everywhere. They can be applied even to our visual system as well. And we might discuss on one of the lectures of webinar or webinars how can actually our visual systems might be attacked. But still, they are really interesting because, for example, nowadays people sometimes speak about them, speaking that they can help to get rid of this total surveillance program where all the cameras are actually now connected to some servers and they just find all people in all the places all the time. For example, some adversarial attack stickers, just real stickers on the paper, for example, can be printed. Then they can be just attached to some kind of backpack, jacket somewhere, and the cameras will be actually attacked in some case, in some terms. So they will be not the cameras themselves, but the algorithms will have much less chances to recognize person on this image. Other problem is that people are still able to see these adversarial attack stickers, and they might ask questions, why are you trying to hide yourself? But actually, that's not about our course today. So there are many different problems. Here is actually illustration of what I was saying right now. We have the detection mechanism, which detects person on the left, but it's actually unable to detect person on the right. And here is this adversarial attack sticker, which is actually breaking the computer vision system. And here, just in case, if you're interested in more materials just right now, you can see that there are a lot of different links in this 1, 2, 3 presentation. You can always touch them, push them, and go to the original paper, original blog post, and so on, where these beautiful images were actually taken. There are actually a lot of different interesting topics discussed over there. We shall discuss almost all of them in this course as well, but later, today we have the overview. All right, let's make a quick summary. So we have different computer vision tasks, and right now we discussed classification, just classical task, localization, just localization of one object on the image, detection, localization of several just variable number of objects on the image, and semantic segmentation, segmentation of one image into just pixels of different entities, or instance segmentation, where we can have pixels assigned to same classes, but still to different entities, like we had motorcycle 1, motorcycle 2, they're actually two different motorcycles. We discussed image generation, adversarial attacks, and actually we'll discuss many more different problems. And the beautiful part is, in all these problems, the main part of the approach is usually the same. Because when I was speaking about computer vision, natural language processing, graph machine learning, and so on, we usually first of all speak about feature extraction. And in all these problems, we usually will have similar feature extractors, and not just similar. In some cases, they will be exactly the same. So the biggest part of our model will be just shared between different problems, and only a tiny bit of the end of this model will be trained and fine-tuned for specific problems. And there are a lot of different problems we will cover later, where you can find actually them on the web, on different blog posts, in different open lectures, and so on. Like image captioning, combination of computer vision and natural language processing, where for every image, the string describing this image should be generated. Image encoding, just way to encode image, maybe to reduce the used size or to reduce some number of noise on it or something like that. Image morphing, just transforming one image into another. Image upscaling, actually making image better in terms of resolution, for example, super resolution. Video object tracking, you have some kind of image and now video sequence of images, and you need to track some object from frame to frame. Video interpolation, like we increase the frame rate for some video. Online learning and scenario construction, many different problems. Actually, if we just try to enumerate them all, I guess we won't be able to do that, and it won't be enough 10 slides, 20 slides to do all of that with this font. All right, so what do we have learned so far? There are many different problems. They are solved somehow with similar methods, just as we discussed right now, but we never discussed how exactly they're being solved. And we have a lot to learn later. So let's move on. And to move on, we actually need to understand how these problems are being solved, at least at the beginning. And to do that, we need to recap what is a convolution layer and how does it work. So just a beautiful illustration of LeNet, neural network from Jan LeCun from 1998, convolutional neural network. It's already more than 20 years old, and it's rather similar to the neural networks which were proposed 10 years ago, for example, AlexNet, which we discussed in the beginning of this lecture. So many of different networks, especially till 2018, I would say, almost all of them till 2019, were based on the convolutional layer and on the convolutional architecture. So let's actually discuss what is a convolutional layer once again, and here is an example. So we have an image. Image is just three-dimensional tensor where we have height, width, and number of channels. We assume that all the channels are independent, and now we want to transform this image, but not using classical linear layer where every new pixel actually is connected with all the previous pixels, but we want to preserve the local structure of our image because we assume that pixels which are staying close to each other are actually somehow connected in terms of the original scene where we have taken this image. For example, if I see my finger in here, then it usually means that other fingers should be somewhere around it. It won't be true all the time. For example, I can show only one finger in the frame and all others are just invisible because they're outside of the frame, but still usually that's true. That's why we propose the convolution operation, which actually convolves the whole original image with tiny filter with some spatial size. And we convolve the original image with this filter to get some activation map. So actually, we just apply this filter to every possible location, just convolve it, make actually a linear operation, multiply image by this filter, and get one number, like here we go. And we get the activation map, where every number is now actually assigned by multiplication of this part of the image and this filter. And when we get it, we just have activation map, which shows us how similar every location of the image is to the filter itself. Because actually, when we do this multiplication, we just compute the dot product between two vectors, between two matrices stretched into vectors. And we can remember that when we are speaking about dot product, we have this cosine similarity and so on, especially when we are speaking about same normed vectors of the same norm. So here is the visualization of this convolution operation. And we have filter of size 3 by 3. We have input of size 4 by 4. So our activation map just will be 2 by 2. I guess it's obvious. And here, just in case, in here we assume that we have only one channel image and one filter. That's why we have only flat input and output. So once again, we have image of size, for example, height, width by number of channels. And our filter, just at the beginning, by design, in the simplest case, has some spatial dimensionality and same number of filters, same number of channels. And it generates especially one channel, exactly one channel on the output. So activation map just now has one channel. What we can do next? We can just say that, all right, we have one filter. Why don't we have 10 of them, 20 of them, 50 of them, just any number? Just like we discussed in self-attention in transformer mechanism, multiple attention heads can generate multiple representations of the original data. Same stuff here. We can have several filters, and different filters will give us different representations, different activation maps, and actually different channels of our updated, not already image, but just hidden latent representation of the original image. And we, of course, take them along the channel dimensionality. So we had some kind of three-dimensional tensor on the input, and we preserve three-dimensional tensor on the output. We just change its spatial dimensionality, so it's usually lower, and we may change the number of channels. So here we go. And here is an example of simple convolutional neural network. So we have some input image, then we use convolution with several layers, with several kernels. Then we use some kind of activation, like ReLU. We get another three-dimensional tensor, use another convolution, ReLU, and so on, until we get some kind of vector, for example, or small image, where we actually can use pooling to get finally vector, And since we got the vector, we can apply all the linear transformations, all the classifiers, all the stuff we had before. So I guess it's kind of fine, and you now remember all the stuff about convolutional neural networks. So what happens next? Actually, when we have extracted some informative feature representation and convolutional neural networks and spoiler transformers for computer vision as well are really capable of extracting some information from the original images. When we get the informative representation of our original image, especially informative vector representation, we can start solving problems, and let's discuss it right now. So let's discuss different famous neural network architectures in computer vision and illustrate them by some pictures and explain why they actually became so famous. First of all, here is just beautiful picture, just overview of different networks achieving some quality on the ImageNet dataset. Just in case, ImageNet is a huge dataset with 10,000 of different classes, and network needs to predict the class correctly. So actually, we have number of parameters over the x-axis, ImageNet top 1 accuracy on the y-axis, and we can see that actually since inception v2, ResNet, DenseNet, exception, and so on, the quality is kind of increasing. So from 74%, for example, for NASANet, and even lower, for example, 73, I guess, for ResNet 34, the quality is now around 84%. And once again, it's top 1 accuracy, and there are 10,000 classes. Kinda a lot. We see that actually the quality increased a lot, and we can see definitely that the number of parameters is increasing as well. And in this case, the number of parameters is actually increasing not so dramatically. For example, if you take a look at what is going on in natural language processing area with these transformers, in there we see something like exponential growth, but we will see it in the other topic, in the other class. So we have different models, and what we can see is that actually deeper networks, by deeper I mean more complex networks, and usually the complexity is increased by making the network deeper, so more layers, more convolutions, more transformations are located in the network. So usually deeper networks show better results, usually, because not always. And of course, deeper networks have many problems. They can face vanishing gradients, like we've seen in LSTMs, GRU, but actually vanishing gradients are present in all possible neural networks which are deep. We can face exploding gradients, so we can get just a really strange, huge gradient, change the parameters too much, and break everything. We can see biased activations. For example, ReLU is actually shifting the output, and that's not so good. We can face some memory issues, like our network is just consuming too much memory and we're unable to deal with it, and so on. And of course, complex networks require more memory, more computational resources, and they just work slower in many cases. Okay. And if the network is complex, of course, it's capable of overfitting really well, because complex network is just great at overfitting. It's one of the main purposes of complex networks. So people have to incorporate some regularization techniques, some informative priors, some restrictions on the network, increase size of the training dataset, and so on, to make the networks train better but not overfit. Here we go. And here is one of the most famous networks in the world. Actually, as far as I remember, at least last year, ResNet, residual network actually, paper on the ResNet, you can see it here, was the most cited paper on deep learning in the world, at least in some domain, because there are many different papers in the world. But ResNet was among one of the most cited papers in the world. And it's rather simple if we take a look at it right now, because ResNet has only one difference from all the previous networks. Okay, one main difference from all the previous networks. It has these beautiful residual blocks where the data node is not only transformed using some weight layers, so some transformations we discussed before, like convolutions, for example, but it also has the identity connection, identity just bypass link, which copies information from here to here, and then the network just sums up the transformed data with identical data, so it preserves some original information and changes it as well. And the most beautiful part of it is that it allows to train deeper networks, especially because it improves vanishing gradient. If you take a look at this architecture and just think about it in terms of gradient computation, you can see that when we get gradient from the end of the network, from the loss function, for example, if we don't have this identity connection, then the gradient will go through this layer, through this layer, through these activations, and actually we have some chance to reduce the gradient at every step. So deeper the network, the smaller the gradient is in general. But when we have this identity connection, the gradient will just bypass these transformations and the gradient will be still preserved. So network will be actually able to train even if it's really deep. And actually that's what happened when the ResNet was proposed. Because before ResNet, the networks were about 30 layers. I am not so sure about exact number. But when ResNet came out in 2015, the biggest network they trained was 152 layers, which is 5 times bigger than, for example, GoogleNet, which had around 30 layers, I guess 22 layers it had. And it already had some problems with training the parameters because the gradients were already vanishing. So ResNet with 150 layers maintained to be achieved great results and was trained while it was really deeper thanks to the residual blocks. And if you take a look at this residual block, you might see that actually it looks really like LSTM memory gate. Okay, not memory gate, just additional memory link, which we had there, because it serves for the same purpose, to preserve some information and to preserve gradients on the backward path, and we can see it in here as well. Funny stuff that actually, and interesting as well, interesting information is that LSTM was presented in 1997, while ResNet was presented in 2015, so almost 18 years of difference, while almost the same idea under the hood. That's kind of beautiful. So, main idea, skip connections, they usually name skip connections, really rock. And here is an example. So here is original, not original, some intermediate representation, several transformations, and here is this residual skip connection, here is a residual block, and here is actually the main transformation, just not transformation, sequence of transformations. So some transformation, skip connection, another transformation, but still skip connection, another transformation, but still skip connection. So actually the network is able to preserve the data from the beginning to the end without losing it. It's really great. And to preserve the gradients from the end to the beginning as well. And actually looking at this approach, one could imagine, and what if we connect not just this output, this input with this output, but what if we connect just everything with everything, literally? Actually, in this case, we'll invent DenseNet, which was already invented back in 2016. And looking at the picture, you can see that actually it's almost the same idea as we have in ResNet, but right now we don't skip only one transformation, but we skip several transformations at one step. So these connections are named dense connections, and DenseNet literally connects each layer to every other layer in a feed-forward fashion. And it just concatenates outputs, so not sum them up, but just concatenate. And it allows, of course, to improve vanishing gradient. It allows to build really informative representations. Of course, we shall discuss them in depth. I mean, these architectures as well. Right now, we're just making the main overview. And DenseNet was really great back in 2016 as well. It had actually one tiny problem. It was really consuming a huge amount of memory, especially for the times. But later, GPUs became a bit cheaper, okay, at least until 2019. And DenseNet was really one of the good choices. And just getting back, here is just several examples of transformations from ResNet. So just here is identity track, here is transformation, there they've been added. Originally, ResNet just had simply addition and activation. Then they incorporated the batch normalization to make everything more stable. And they experimented with this architecture a lot. So they tried to actually add batch norm after the addition, batch norm ReLU, or add it within this transformation. So in here we have only addition, or actually change the order to put ReLU, for example, at the beginning. So there were a lot of different ways to construct this network. And why do we have actually this slide here? Reason is relatively simple. To show you that actually when people are designing new architectures, they are actually looking for the best architecture, not by solving some optimization problem just out of the box, but by experimenting a lot as well. And that's why actually deep learning nowadays is usually traded in many areas like engineering just area, because people just try many different approaches to find the optimal one, then write some paper, present it on neural IPS, and so on. Because we don't have enough mathematical apparatus, and I'm not sure whether we'll find it in the upcoming years, to find optimal architectures just out of the box as a solution of some optimization problem. All right, here is the RESTnet, main idea, skip connections. Here is DenseNet, main idea, dense connections, almost the same as skip connections. And here is just another example of DenseNet. So input, then we have convolution, then first dense block where everything is connected with everything, then convolution and pooling, then second dense block, another convolution pooling, third dense block, and finally pooling and linear layer, because since here we have only vector representation of our vector. And in the end, it just predicts class labels, for example, like it's described in the original paper. Once again, highly recommended to read this paper. Okay, and now let's speak a bit more about convolutions. We already discussed what are they, but are they really that great? We discussed right now. Of course they're great, but maybe we can make them a bit better. First of all, what do we have? We have normal convolution, and it uses all input channels. For example, we have three channels on the input. So we have convolutional kernel, which has 3 channels as well. And when we just convolve this kernel with this image, we get 1 channel output, 1 channel activation map. So for example, if we use 256 different convolutional kernels, then we'll get this 256 channel output, and that will be it. But what if all the channels are actually, not all, but some of the channels are redundant? Why should we use all of them in every kernel, for example? Actually, here is an idea. So kernel might be factorized by channels, so we get depth-wise convolution, or spatially, so we get separable convolution. And let me just give you the brief introduction of depth-wise and separable convolutions and explain what's going on. And the main goal is just to get smaller memory footprint and reduce number of flops, floating point operations per second, to make our networks actually smaller, quicker, better, stronger, and so on. So here is first idea, depth-wise convolutions. Actually, the idea was relatively simple, and authors proposed to use separate kernel for every channel. So now actually we use only one kernel of the same size. So we have 3 channels here, so we have 3 channels in the kernel, but actually every channel now has its own kernel, and we only apply this kernel once to preserve number of channels and actually to work with every channel separately. Just the idea. So we deal with every channel separately, and the orange channel is transformed only into orange channel. It does not affect red channel. Red channel is transformed into red, and it does not affect yellow and orange, and so on. And the idea beneath it is actually that different channels, especially in deeper parts of the network, usually define some specific properties of this specific location on the image, which are not usually highly connected with each other. Okay, not usually, but sometimes. They're not really connected, they're independent in some terms. That's why we can just interact with them separately. And speaking about separable convolutions, it's another beautiful idea. So when we have some matrix, actually this is a filter, this is kernel of our convolution, we can always actually factorize it and use 2 vectors, which, if we multiply them, will give us the same matrix we had on the input. So actually we can try using this separable convolution, where first we convolve our image with 3 by 1 kernel, just with this vector actually, okay, matrix with 1 column, and then we convolve this intermediate image, actually it's not already an image but some kind of latent representation, with another kernel, now of vector, not column vector but row vector, and finally we get the output image. And now we can see that filter size is not c by k, but c by k by 2. So it requires small amount of parameters, it has smaller chances to overfit, and it is just quicker. And once again, here is the idea. We can reduce number of channels, we can reduce number of filters, we can reduce number of parameters we use here, and also we can just reduce number of channels explicitly. For example, we have 3 different channels on the input, and we can just apply one-by-one convolution or pointwise convolution, which just interacts with all the channels in every pixel. So this convolution actually ignores the local connectivity of pixels, and actually it is a linear layer applied to the channel space. If you just take a look in here, so we convolve this part of the image, all pixels, sorry, 1 pixel for every channel, we convolve it with this kernel. So actually we just multiply this vector by this vector to get this number. So actually it is exactly linear layer, and that's why even fully connected neural networks where no linear layers are present can be used for image classification, because in there, instead of linear layer, people are using the one-by-one or pointwise convolutions. All right, so here we go. And just to briefly combine everything together, we can compare convolutions by kernel size. Like normal kernel size will be c by k by number of actual channels. Depth-wise, then we have only one channel. Okay, not one channel, but every channel is transformed into another channel, but we preserve number of channels. We can use separable convolution, so it actually has small amount of parameters. We can use pointwise convolution. Actually, it only transforms channels into other channels, but it ignores all the structural information within our data, all the spatial information. And we, of course, can combine all these approaches together to get smaller, quicker convolutions. And actually, that's what happened back in 2017 in MobileNet. MobileNet, I guess it's kind of obvious, was designed for some mobile phones because they really don't have a lot of computational power, and especially they don't have a lot of battery power, so they can work a lot for a long time with complex networks. So MobileNet actually used 3x3 depth-wise convolution and then one-by-one convolution instead of using original 3x3 convolution to reduce number of parameters but to achieve same performance. So once again, the idea was to split 3x3 convolution into 2 parts: depth-wise convolution and point-wise convolution, where they actually reduced number of operations, number of parameters, but still preserved almost the same behavior and same quality. And it's used in low power devices. Okay, right now MobileNet is not widely used because there is actually MobileNet version 2, and actually right now there is even MobileNet version 3. And MobileNet version 2 is almost the same as MobileNet from 2017. They just used several different convolutions. So they used separable convolution, separable with linear bottleneck, bottleneck with expansion layer, and so on. And here is the original paper. Once again, here we only make an overview of different architectures. The specific properties of some of them will be covered later. And in 2018, squeeze and excitation networks came out. So they actually provided some new approach to images in terms of using global pooling and then just dealing with some vector representation of the image instead of using only some max pooling or average pooling in some patch of the image. And using actually linear layers instead of convolutions, because as soon as we get vector representation, we don't need convolutions anymore. We can use just linear layers. And these networks actually used global averages of feature maps for better classification. They really achieved good results in classification. And they just scaled feature map channels and excited useful information. So they tried to select useful information, suppress redundant information, and this paper is really interesting to read as well. So usually this approach is applied in the later layers of our convolutional neural networks, because in the first layers we still have a lot of spatial information, and if we use global pooling, then we get rid of this information just instantly. All right, and finally EfficientNet from 2018, actually, or from 2019, there are several versions. EfficientNet is actually EfficientNet because people tried to find really efficient network for image classification, segmentation, and so on. And it has several features because authors tried to scale model both by varying the depth, number of layers, varying the number of channels, representing the image at every step, varying the input resolution, because many problems can be solved on lower resolution, for example, some segmentation, especially not segmentation, sorry, detection, for example. And they use compound scaling for better performance. But mostly interesting, they also use the neural architecture search, actually NAS and AS. Neural architecture search is sub-area of deep learning where people try to use some techniques to find optimal architecture of neural network. And it's really a problem because when we try to find optimal architecture, we are now speaking about some non-differentiable problem. We're speaking about some graph prediction, and that's why we cannot use classical methods like gradient descent out of the box in this problem. So EfficientNet actually achieved a lot of results, and with EfficientNet we just finished our brief overview of different architectures, because right now, because we can actually speak about YOLO, 1, 2, 3, 4, 5, YOLO for you only look once. You can speak about AmoebaNet, which was actually on the previous pictures, for example, where it was. Amoeba, please come back. Okay, sorry, one time, yeah, here it is, AmoebaNet. For example, I guess it was generated by neural architecture search as well. But right now, let's just finish with the architectures overview, because just broad overview, and speak about one additional really important stuff, about datasets. Because even if you have the best architecture, with no data, this architecture is useless. So everything started a long time ago, actually maybe with MNIST, maybe with CIFAR 10 and CIFAR 100. So it's a relatively small dataset. We shall see it on one of the practical assignments. And it contains just small, really tiny amount of images, like 60,000 of images, 32 by 32. At least they're colorful compared to MNIST, for example. There are only 10 classes, like airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, truck, and that's it. And only 6,000 images per class. Or you can have 100 classes, just a bit splitting different classes into subclasses. And then there are only 600 images per class, so compared to nowadays, it's just really small. But CIFAR was actually presented in the previous century, so that's absolutely fine. So, speaking about more popular datasets right now, there is a Pascal dataset, Pascal Walk 2012. Actually, it's been developed since 2005. It contains only 11.5 images with 20 classes, but now it has not only class labels, but it has detections and detection, bounding boxes, and segmentation maps as well. And images I actually parsed from Flickr.com, so several services actually help deep learning and science at all. And just in case, walk for visual object classes. So there is ImageNet, which is actually really popular, beautiful, and actually when we were speaking about AlexNet, actually AlexNet network from 2012 achieved to beat everything else on ImageNet. And ImageNet has around 14.5 million images. It has 1,000 and later 10,000 classes. So it has 1 million images with bounding boxes around different objects. And it has diverse object properties. And what's beautiful, actually, it has WordNet hierarchy. If you remember from the natural language processing class, WordNet is this graph connecting different entities with different words with different types of relations. So on WordNet, you can actually connect different objects with different properties. And on ImageNet, you have different images which are somehow labeled. So labels are words. So from there, we can get the connections between them. Okay, here we go. And finally, speaking about recent datasets which are used nowadays to train some new networks. For example, MS-CoCo from 2017. It has around 330,000 of images. It has 91 object categories, but actually it's used for semantic segmentation and object localization, and detection is segmentation, classification, and so on. So these images are not just labeled with some word, with some class label, but instead of that, they have localization, they have instance segmentation maps, bounding boxes, and so on. And MS-CoCo is usually used to train, to fine-tune, or to train from scratch some models, even nowadays, because this dataset is rather new. Okay. And just simple statistics. So here is CoCo statistic, Pascal with orange, ImageNet with something like purple, and Sun dataset, we never discussed it yet. but still, we can see that actually we have about for cocoa, we have about 20% of images with one category on them. Most of images have 2 or 3 categories on them, and then we don't have almost any images with 15 or 10 or more categories on them. We have usually about 1, 2, 3, 4, 5, 6, or 7 instances on every image. So it's not one instance per image like we have on ImageNet or Pascal, as you can see here. And actually, that's kind of interesting. And another beautiful dataset, actually Open Images, it's currently one of the most relevant challenges. It has 15 million bounding boxes of 600 categories. It has almost 3 million instance segmentation maps on 350 categories, and it has 36.5 million image level labels on 20,000 categories. So it's kind of really beautiful, and in addition, it has almost 400,000 relationship annotations of different types of relationships. And here are just example images from these datasets. Like here, they have several dogs, several cars, several furniture pieces, person, bicycle, child, different people on the same image, localization. Actually, in here, they even have all the windows labeled and so on. So this dataset is one of the most relevant nowadays. If you want to train some model from scratch and you need some image data, try thinking about this dataset as well. You can access it via this link. And once again, just some statistics. You can see that Open Images has many images with many objects, even about 4% of images with 10 or more objects. That's kind of great. And almost all objects cover more than 10% of the image area, so they're not too small, except in this situation, I guess, because these windows are really small. And it has really beautiful relations between images, like we can see here. So we have images of sports equipments. There are different sport equipments like helmet, racket, bicycle, ball. So this label is split into sublabels. Then these sublabels might be split into other sublabels and so on. So actually there are different labels which are not just stored separately somewhere, but they have some kind of hierarchy, and it can actually help us to build informative representation of images as well. All right, actually that's almost it about the datasets. And finally, let's finish this lecture with a small overview. While we're speaking about really recent, beautiful modern architectures, old problems like vanishing gradient, exploding gradient, like overfitting, all these problems are still present, and we still need to think about them and fix them somehow. We should nowadays think not only about making models bigger, deeper, and so on, but scaling them and making them smaller as well, because we don't have enough computational resources to run on the models at the same time. And beautiful idea about convolutional neural networks is that convolutional layer might be factorized itself to reduce number of operations we need to compute something. Datasets are actually getting bigger, that's great, but models are getting bigger even quicker, and that's kind of a problem. And there are a lot of computer vision tests yet to be solved, so if you feel that you're interested in this area, feel free to ask any questions, dive deeper, read the papers. We have links in this presentation, and take care. Actually, that's the end of this lecture. Thank you for being here today, even in online format. See you next time, and hope you'll be fine. Good luck.